Okay, let's talk about ionic size. And you know ions. Ions are charged species. These are just charged species. And what we're really talking about, atomic ions, all right? If it's a cation, it's going to be a metal that has lost electrons, all right? And it'll have a positive charge. Cations have lost electrons, they've been oxidized, they have positive charge. So here's the deal. No general periodic trend, but you're going to compare the atom to its respective ion. So here's sodium. Let's take a look at the electron configuration for sodium. And we notice that it's got this 3s1 electron. Well, sodium's in group 1, and all the group 1 elements, the alkali metals, they love to give up that 1 electron. All right, so for the atom, we're thinking there's the nucleus, there's n equals 1, there's n equals 2, and way out here we've got n equals 3. That's the valence shell for a sodium atom. And when it oxidizes, it's going to lose that entire valence shell. So the cation, which has a +1 charge, you got the nucleus here, you've got n equals 1 and n equals 2. And you can see that it's lost that entire valence shell. It now has a positive charge, and it is definitely smaller as a cation than it was as an atom. So cations will be smaller than their atoms. Smaller cations, atoms will be larger, and you can see that it's lost an entire valence shell. Anions go the other way, okay? If cations are smaller than their atoms, anions are larger than their atoms. So we're just going to compare atoms to ions, and here's the deal. This is oxygen, and it has 8 protons in the nucleus. And those 8 protons are pulling on 2, 4, 8. Plus 4 is 8. It's pulling on 8 electrons. And it's at the valence shell this is n equals 2. Okay, there's your n value, n equals 2. We're still at n equals 2. However, now we've got an extra 2 electrons. So this is going to be 8 protons pulling on, having to hold in now not 8 electrons, but 10 electrons. And each electron gets a little bit less love from that positively charged nucleus. And so these guys, you can just think of it this way. I'll do it right here. Here is the atom of oxygen, and when you add those 2 electrons, it swells up. I kind of like to think of it as going to a wedding reception, and you're sitting at a round table. Somebody brings a couple of uninvited guests, and so everybody has to sit further away from the center of the table just so that they're not bumping elbows, because everything gets to expand, okay? So if for anions, atoms are smaller and anions are larger. It's exactly the opposite of the way cations and their atoms are. Cations are smaller than their atoms, anions are larger than their atoms. Okay, and there's what we just talked about. 8 protons, 8 electrons, 8 protons, 10 electrons. The anion swells up a bit, okay? It gets larger. So for anions, atoms are smaller than their anions. Okay, so this is just a visual, so you can visualize it. Atoms lose electrons, the cations are smaller, and for anions, the atom gains electrons and the anions are larger. Okay, for a cation, the atom will be larger than the corresponding ion, and for anions, the atom will be smaller than the corresponding anion. This is just a general trend in atomic size. I'll just do two. Here's the lithium atom at 1.34 angstroms and lithium cation 0.68, much smaller. And over here for fluorine and fluoride, the fluoride ion, 1.33 angstroms, and the fluorine atom, 0.71 angstroms. Last time, anions are larger than their atoms. The gray guys right here, those are the atoms. The blue guys over here are the anions. And for cations, exactly the opposite. Atoms are larger than their cations. All right, let's talk briefly about atomic radii and isoelectronic series. I'll see if I can load that up. It's probably already on track, so I'll send you the link. But let's just talk about isoelectronic series. Iso means the same. And since we're talking about electronic, we're talking about the same number of electrons. That's what an isoelectronic series is. The same number, some species that have the same number of electrons. They don't necessarily have the same number of protons, however. So here's sulfur. It has 16 protons in the nucleus. Chloride ion has 17 protons in the nucleus. Argon has 18 protons in the nucleus. Potassium has 19 protons in the nucleus, and calcium has 20 protons in the nucleus. We're going to think about this with respect to effective nuclear charge. Let's start with argon. It's a neutral atom, so it not only has 18 protons, it has 18 electrons surrounding the nucleus. Let's go to the anion side first. This is chloride ion. So you've added one electron. So a chlorine atom would have 17 electrons, but a chloride ion has 18 electrons. Here is the sulfide ion, 16 protons, but you've got a 2- charge, so it also has 18 electrons. I think you can see the way this is going to go. And here we have given up one electron for potassium. It goes from 19 electrons as an atom to 18 electrons as a cation. Calcium's going to give up 2. It goes from 20 electrons as an atom to 18 electrons as a cation. So how come calcium, which is definitely heavier, is smaller than sulfide ion? And why is the trend go from smallest to largest? Well, remember, effective nuclear charge. The effective nuclear charge is equal to the number of protons, we call that Z, minus the number of shielding electrons, and that's just the electrons that are in the core, the ones that are in the way. And if it's got 18 electrons for each one of these species, they all have exactly the same electron configuration. They have the electron configuration of argon. But with more protons in the nucleus pulling on the same 18 electrons, calcium pulls those electrons in tighter, and so it makes a smaller radius. Sulfide ion, on the other hand, with only 16 protons pulling on those 18 electrons, lets them drift out further away. All right, so this is an isoelectronic series. The way you figure out which one's smallest to largest, the smallest will have the highest number of protons, and the largest will have the fewest number of protons.